So welcome to the end of chapter 3. There are 3 sections in chapter 3, and we're going to introduce the final section today. And there's a lot of stuff in there, so let's see how far we can get. There's 39 slides. I don't think we'll get through all of them. So again, chapter 3 is describing, exploring, and comparing data. And in the first section, we introduced measures of center, which were things like mean, median, those sort of ways of having a calculation that gives an answer that's around the middle of what we expect for the data values. Then we looked at measures of variation, and the key thing was standard deviation is sort of the most important. There are other things like range and stuff, but standard deviation was very, very important. And so in this third section, we're looking at measures of relative standing and box plots, which is a kind of graph, a new kind of graph that sort of also in the graph shows the spread of the data in a special way. So what's our key concept? This section introduces measures of relative standing, which are numbers showing the location of data values relative to the other data values within the same data set. So a simplest example of something like this is if I were to give you a data value and say that's the maximum data value in the set, then not only are you seeing what the data value is, but because of the description, you know that it's the biggest one and that all the other data values are smaller than that. So that description is not only saying the value, but how it relates or how it is relative to the other values within the same data set. And we're going to go into much more detailed ways to do that for different data values. However, the most important concept, and they cannot emphasize that enough, in this section is the Z-score. We're introducing the Z-score. And again, it's in bold, and you have no reason to know what that means at this point. So we will define it in the coming slides, but it is the most important concept, and we will be using that throughout the rest of the semester. Now, we also will be discussing percentiles, quartiles, which are common statistics, as well as another statistical graph called a box plot. But the Z-score is super important. So those are the key concepts for the section. So let's start with this all-important Z-score, the most important concept of the section. A Z-score or standard score or standardized value is the number of standard deviations that a given value X, meaning a given data value, is above or below the mean value for the data set. This Z-score is calculated by using one of the following, and they're going to say you can get a Z-score for a sample data set, or you can get a Z-score for a whole population for a parameter, for a particular value of a parameter. So to come to terms with what this means, how many standard deviations above or below the mean, we can probably look at some examples and some graphical picture of this. But it says briefly, round off rule for Z-scores. When Z-scores are calculated, you round them off to 2 decimals, and this will be how they show up in tables and things like that. Properties of Z-scores. So let's look at this with me giving an example to have that in mind to illustrate the concepts of the properties of what makes a Z-score what it is. So again, what is a Z-score? Is the number of standard deviations that a given value X is above or below the mean. So let's say we'll go back to my classic example of students at DVC and how tall they are. And let's say that I take a sample of 100 students and I get a mean height of 5'8". And let's say I get a standard deviation of 3 inches. So that means the mean average, the mean height of the students of my sample was 5'8". And that, if you remember from our range rule of thumb for standard deviation, if my standard deviation were 3 inches, then if I go above or below by 2 standard deviations, if a standard deviation is 3 inches, 2 standard deviations would be 6 inches. That means at 5'8", if I go 6 inches above that and down to 6 inches below that, I create a range of height values where 95% of my sample fell in that range. So 6 inches above 5'8" would be like 6'2". 6 inches below would be like 5'2". That would mean because the mean was 5'8" and the standard deviation was 3 inches of my sample, that the range of height values between 5'2" and 6'2", 95 out of the 100 people that I sampled approximately would fall in that height range. And that only 5% would either be below 5'2" or above 6'2". So the idea of being 2 standard deviations above the mean when I got to 6'2", well, that means that height of 6'2", because it is 2 standard deviations above the mean, it has a z-score of 2. So again, what it says here is the z-score is the number of standard deviations that a given value is above or below the mean. So if my standard deviation is 3 inches and my mean is 5'8", then if I add 3 inches to 5'8" and get 5'11", that would be 1 standard deviation above the mean. And that means that 5'11" would have a z-score of 1. 6'2" would have a z-score of 2, being 2 standard deviations above the mean. The z-score labels how far away from the mean a value is by counting how many standard deviations you moved away from the mean to get to that value. When I go below the mean, then the z-score will take on a negative value, indicating that I subtracted that amount to get to that value. So for example, with 5'8", if I subtract 3 inches, I get 5'5". I think that's my height. So that means that my height, 5'5", would have a z-score of -1 because it is 1 standard deviation below the mean. So that's what the z-score is. It's a score assigned to a particular data value that tells you how far away from it is above or below the mean by counting by how many standard deviations you had to go to get there. Now, if it's a nice whole value and the standard deviation is a simple thing like 3 inches, you can use some simple examples pretty quickly. But you could be 1.23 standard deviations above the mean. You could be some multiple value above or below the mean that's not a nice whole number, but is in fact some decimal value. So let's read through the rest of these properties with that idea in mind, and then let's see if we can have some discussion about this. Z-scores are expressed as numbers with no units of measurement. So it's not going to be feet or inches because it's how far away you are from the mean in terms of standard deviations, and you're just going to give that value. A data value is significantly low if it has a z-score less than or equal to -2, and significantly high if its z-score is greater than or equal to +2. And this matches exactly within the previous section in 3.2, where we talked about significantly high or low values being more or less than 2 standard deviations away from the mean. That would mean that they have a z-score bigger than 2 or less than -2. If an individual data value is less than the mean, its corresponding z-score is a negative number. And if it's greater, it's a positive number. Questions, comments, discussions about that? Okay, here's a challenge. Try to imagine in your mind an example where you had some set of data, some measurement, numerical, what the mean value was, and again, you can make these up, but just try to imagine them with specifics. You have a mean value, and you have a standard deviation value. And then try to think of the value in the data set that would have a z-score of 2. And if you're willing to share your example, please speak up or put it into the chat. So try to think of an example of a data set, what the mean and standard deviation are for that data set, and what value in the data set would have a z-score of 2. And if you have questions before you can do that, feel free. Ask away. Yeah, samples coming up next, so let's stay here. All right, if you're a little too lost for that, how about someone give me an example of a numerical data set, and then I'll do the rest with your example. Okay, that's a good example. Age of students at DVC. So let's say that the mean value was 22 years old. And let's say the standard deviation was 1 year. Mean value of 22, standard deviation of 1 year. So then what would be an age of a student to have a z-score of 2?
24.
24. And a z-score of -1?
21.
Exactly. So z-score is going to be something we refer to a lot, and it's really helpful if it becomes something that you're familiar with, and that when you see a z-score, you can think to yourself whether that z-score is big or small, whether it represents, as described in this properties here, a significantly high data value or not significantly high or low. All right, let's look at their example. Comparing a baby's weight and an adult body temperature. Which of the following two data values is more extreme relative to the data set from which it came? The 4,000 gram weight of a newborn baby among 400 weights with sample mean of 3152 grams and sample standard deviation of 693.4. Or instead, a 99-degree Fahrenheit temperature of an adult among 106 adults with sample mean of 98.2 degrees Fahrenheit and sample standard deviation of 0.62. So this will be something where we would calculate the z-score in each case, and then by comparing which has a bigger sized z-score, we can see which value is further away from the mean in terms of how many standard deviations, and therefore considered more extreme. But if you notice, if you don't have this scoring method, this z-score in place, it's really hard to answer the question. It's really hard to understand how extreme a data value is just by observing mean, standard deviation, and the score that you're interested in. So that's what the z-score does for us. It gives us a way to give a common numerical measurement that we can compare within different data sets of size and value and everything. So they're going to do this for us. They're going to basically show how would we calculate this z-score. Well, to see how many standard deviations away from the mean you are, there's a little formula, and you're probably going to use this little formula as opposed to trying to do something like this in StatCrunch, because it's very quick and simple, can be done on a standard calculator, as well as the fact that it helps you understand what you're calculating. So if I want to know how many standard deviations 4,000 grams is away from a mean of 3152, and the standard deviation size is 693, what you do is you first say, well, how far is 4,000 grams from the mean by taking the difference of those two. In the formula, that's x minus the mean value of x. So that tells you how far in grams the value is from the mean, but then you want to measure how many standard deviations that is, so you divide that difference by how much one standard deviation is in grams. And in this case, we get a z-score of 1.22. So that means that 4,000 grams as a weight is 1.22 standard deviations away from the mean value of the weights. Now, when they do the same thing for temperature, you'd say, all right, the measured temperature was 99 degrees. How far away from that is the mean? And then divide that by how much a standard deviation is. And then you get a z-score of 1.29. So that means that the body temperature, when compared to the mean in the set of data values, was a little bit farther away in terms of how many standard deviations from the mean than the birth weight was. And so that would make the body temperature measurement, as those measurements go, a little bit more extreme of a body temperature measurement than the weight was as a birth weight. Questions, comments, discussions about that? So they draw that conclusion here by showing that they got those z-scores and sort of interpreting what they mean. And then at the end, they say the body temperature is slightly more extreme than the birth weight. So a z-score is a number that tells you how extreme a data value is compared to the other datas in the set, and therefore how sort of likely or unlikely to get that kind of a number you'll get. So when they say significantly high or significantly low, that also begins to mean a little bit harder to get, a little bit more rare if you were just looking over the data set. So they give a little graph of this, and you may remember that this graph is like the one they used in the previous section, but instead of having z-scores, they talked about how many standard deviations something was, and that just wasn't measured with a score. And as you may recall, 95% of the data falls typically within 2 standard deviations of the mean, and that only leaves 2.5% to be significantly high and another 2.5% to be significantly low. And now we can attach z-scores to those significantly high and low values. So significant values are those with z-scores less than 2 standard deviations, or less than -2 for the z-score, or greater than +2 for the z-score. So they're going to do another example, and I'm going to go ahead and let you guys check this out. It basically does the same thing where they calculate the z-score. They got -2.56, so that means it's about 2.5 standard deviations below the mean. That's going to be significantly low because it's below -2, and they draw that conclusion. All right, so that's their z-score description, and that is the most important concept. You have to get used to it, do some of those little z-score calculations, but let's see if we can move on and introduce some of the other concepts in this third section of chapter 3. So the next thing we look at, which is more precise measurement of where something is in a data set, is called percentiles. Percentiles are measurements of location, denoted P sub 1 up through P sub 99, which divide a set of data into 100 groups with about 1% of the values in each group. So you have these list of numbers, and there's 99 of them because the first one is p sub 1 and the last one is p sub 99. There's 99 of them, and those are little divider markers. And then the idea is they divide up. There's one above the top one and one below the bottom one, and those divide this data set up into groups where there's 1% of the data values in each of those groups. And if you have a large data set, like let's say you had 1,000 data values, then maybe something like 10 would be in each of those 1% groups. For example, if I went to P99, that would be a place in the data where 1% or 10 of those 1,000 data values were bigger than P99, maybe perhaps equal to P99. So that's the idea. Let's see if we can explore this a little better. How do I find a percentile of a data value? Well, the way you do it is basically see as a percentage what percent of the data set is below the one you're looking at. So the process of finding the percentile that corresponds to a particular data value X is given by the following. And you want to round off to the nearest whole percentage. The percentile of a data value X is you take the number of the data values that are less than that one and divide by all the number of the data values. That'll give you the portion of the data values that were below that one. And you multiply that as a decimal by 100 to move the decimal over 2 places and get a percentage. So a simple example would be if I looked at the median. You may recall the median is the value right in the middle of the data, where half the data is below it and half is above it. So that means if I took the number of data values below the median and divided by the number of data values altogether, I would get 1/2, because half is below the median. And then I would multiply that 1/2 times 1/2, and I would get 50%. 0.5 moved over 2 decimals is 50%. So that means the median, the percentile of the median is a 50%, and that means that's P sub 50. The median value is equal to P sub 50. It's the 50th percentile data point.
Would you use the median as the number of values less than X?
So the median will be a number like 5'8". The number of values less than X would be when you count up how many of the data values in the set are below the particular 5'8" or whatever the median value of your set is. Now, if it's the median, because the way we define median, you know that half of the data values will be below that. If there were 1,000 data values, then 500 would be below the median. If there was 70 data values, then 35 of them would be below the median, because the median's right in the middle. Does that make sense?
Yes, thank you.
Good question. So in the case of 35 out of 70, that means I would get 35 less than the median. I would divide by 70. That's all the data values. And that would give me 0.50. And I would multiply by 100 and get 50. The median will be the 50th percentile because it's the place where 50% is below. But let's look at an example. So here they're giving us a data set, and if we tally these up, I think you'll see there are 50 data values here. This is a 5x10 rectangular set of data. And it says these are Airport Verizon cell phone data speeds listed below, and they're arranged in increasing order. That's very nice. They've made them smallest to biggest for us. Find the percentile for the data speed of 11.8 megabits per second. So I think they're going to do some of this for us in the following slides, but let's think about working this together. So first thing I would do is I would say they want 11.8. Where is that? That's right there. And on my list, all the stuff above there are the ones that are less than that because the list is arranged from lowest to highest. So that means that there are 20 values less than 11.8. And as I just observed, there are 50 values altogether So what I would do is I would say there are 20 values that are less. There are 50 values altogether. That's the portion of the data that's less than the 11.8. And then I would multiply that by 100 to convert it into a percentage, to find what the percentile is for that data value. 20 divided by 50 or 2 divided by 5 as a decimal is 0.4. And if I multiply that by 100, I'll get 40. So that means that this data value is the 40th percentile, because 40% of the data set is less than that one. Question?
Mr. Willett, I mean, actually, it looks like, because it has the 11.8 there in the middle for some reason, but it looks like there are more that are below 11.8.
Yes, 40%, well, below, not meaning above or below on this graph, but below in value.
Oh, right.
20 values less than 11.8, meaning lower numbers.
Oh,
Sorry about that direction confusion there. Is that making more sense now?
yeah, never mind. I mean, thanks.
Yeah, so specifically it's these top two rows that have values lower or below 11.8 in value, and there's 20 of those. All right, so I think they'll do this for us, but I think it's nicer if we can see it there. So they said from the sorted list, we see there are 20 data value speeds less than 11.8. So they use the little formula to say 20 out of 50 times 100 is 40. So then they interpret that and they say a data speed of 11.8 is in the 40th percentile. This can be interpreted loosely as a data speed of 11.8 megabits per second separates the lowest 40% of values from the highest 60% of values. We have P sub 40. That kind of was a very badly made slide because they put the sub on the next line. P sub 40, there should be a P over here. P sub 40 is equal to 11.8. Questions, comments, discussions about that? All right, so let's say, just while we're thinking about it, imagine putting yourself in the driver's seat. Let's say you were asked a question similar to this, but they gave you a data set in a homework problem with 50 data values, and they didn't put them in this nice box arranged in order. In fact, maybe they were in random order, and you were asked to find the percentile of a particular data value. So I want to remind us that what we can do in StatCrunch is move the data in StatCrunch and it'll put them all in one column. And then you can sort that column from lowest to biggest in ascending order. And then you could easily go down the list to find your data value, because then it would be arranged in order. And the row number would tell you how far you were. So in this case, since this was the 21st data value, if I listed these in order in rows in StatCrunch down one column, then this would show up at number 21. And that means I know that the 20 values above it are below that. So if you were trying to figure out what portion or how many of the data values were below a specific value, and all you had was a data set that wasn't organized, StatCrunch would make this easy for you. Put the data values in StatCrunch, arrange them from lowest to biggest, then you can just find your data value, look it up on the list, and the row will tell you how many data values were lower than that value. Questions, comments about that? So they'll give a little bit of notation here. N is the total number of values in the set. K now they're going to use as the percentile being used, like 25th percentile. We just saw 40th percentile. That'll be a K number. L locator that gives the position of a value. For example, the 12th value in the sorted list is 12. And P sub K for the kth percentile is the 25th percentile, the actual number itself. So in the example we looked at, P sub 40 was 11.8. And L would have been 21. That number was the 21th in the position of the sorted list. And N would have been 50. So the formula you get basically is kind of like L minus 1 over N times 100, but nobody wants a formula. You'll just do it. So they have a little sort of flow chart procedure for how to convert a percentile into a data value. And I'm going to leave this for you to kind of look over and see if it's helpful. Notice the formula is there. You can see these little formulas. But I want to move on because I want to introduce a box plot and still have time to jump over to our homework set. And we don't have too much time. So I'm going to leave this for you to peruse in more detail on your own. And you can always come back to me with questions later. So they have the process for converting a percentile into a particular data value. So we took a data value and made it into a percentile. Now they're going to show you how to make a percentile into a data value. And they do that with 4 slides. And again, I'm going to cruise through these to try to get to the later topic of box plot and a 5-number summary. But go ahead and look through this process. Hopefully it'll make sense to you. And again, I got office hour tomorrow night or at 10 a.m. on Thursday before class, if you do end up with questions that you haven't been able to resolve yourself. But they do kind of walk you through it. So hopefully that'll be helpful. And now let's get to the next definitions that we want to finish with in this introduction. So quartiles are measures of location denoted by Q1, Q2, and Q3, which divide a set of data into 4 groups with about 25% of the values in each group. Do they do a graphic of that? No. So let's just try to visualize that. So imagine I have sort of data values spread out across a distribution. And you can imagine a histogram or a dot plot or different ways. But imagine that I cut it right in the middle here. So if I cut it right in the middle, that would be the median. And that would mean that 50% is below and 50% is above. But let's say I take those 2 groups of 50% of the data and I cut those in half as well. That's how I'm going to get down to these 25% chunks. And it may not be perfectly symmetric. So I'm going to try to illustrate that. So here I'm at the 50% mark. And so let's say I went over here and I was at the 25% mark. And let's say I went here and I was at the 75% mark. What that would mean is that 25% mark is that there's 25% of the data is to the left of that value. And then because between 25 and 50% was in the next gap, 25% was in the next gap there. And if I work my way up, all 100% has been separated into these 4 groups with 25% in each. These are the value positions that the quartiles here are referring to. So whatever this value at the 25% mark would be, that would be Q1. This would be Q2. And this would be Q3. And so we can remind ourselves that at the 50% mark is the median. So that means that Q2, because it's at the halfway point, is the median for the set. But we're kind of getting 2 more medians. We're getting a median for the bottom half and a median for the top half. And that gives us these 3 quartiles. And then somewhere over here, you'd have like a maximum value. And then whatever this was at the end down here would be the minimum value. Questions, comments, discussions about what quartiles are? So using our new notation, that means that you can think of P3 as, I'm sorry, Q sub 3 as the 75th percentile. As we were discussing earlier, you can think of the median as P sub 50, the 50th percentile, and now we can also recognize this is also referred to as Q2. And then Q1 would be the 25th percentile, or P sub 25. So if you take these 5 things, if you take the minimum value, Q1, Q2, Q3, and the maximum value, those are 5 numbers that sort of show you the lowest point, the highest point, and the 25% cutoff points along the way of any data set. So those 5 numbers are referred to as a 5-number summary. And they're about to introduce that in the next slides. But while we're sort of putting this all together visually, you have these quartiles, which are the basically 25th, 50th, and 75th percentile points. You can go down to the min and the max, and if you put all 5 of those together, you get a 5-number summary. So as it points out, as I was just describing, the first quartile is the same value as P sub 25. It's the 25th percentile. And it separates the bottom 25% from the sorted values from the top 75%. Q2 is the same as P50 and is the same as the median, and it separates the bottom 50% from the top 50%. So they're describing what I was just telling you, but they're using sentences instead of a picture. And I think that's less helpful, but nonetheless, they're saying the same thing. And then finally, Q sub 3 is P75. And it says, just as there is not universal agreement on a procedure for finding percentiles, there is not universal agreement on a single procedure for calculating quartiles, and different technologies often yield slightly different results, which is true. There's a warning. I think we're going to be pretty good with StatCrunch, but we'll see. So now they're going to throw some more vocabulary words at you. Inner quartile range. This one will show up because that's also going to be used to define outliers. So that's why this will show up, the IQR. But it's basically the range of values that holds the middle 50% between Q1 and Q3. The semi-inner quartile range is just that divided by 2. I've almost never seen that used, but there it is. The mid-quartile range is the average between Q1 and Q2 because that may be different from the median. Very rarely used, not really much of our work. And the 1090 quartile range is the range of values where you get the middle 80%. You can ignore the 10% on the bottom, you can ignore the 10% on the top, and you get the middle 80%. That's the 1090 quartile range. The first one I'm highlighting because you're going to want to refer back to that one regularly. The other ones, not so much. So here they introduce what I just described a second ago when I had the nice picture to do it, the 5-number summary, and they take the 3 quartiles and they add the minimum and the maximum and they put them in order, and that's the 5-number summary. Where does the data start? How far do you need to go up for the first quarter of the data? How far to get to the median? How far to get to the 3/4 point? And then where's the max? That's the 5-number summary. Questions, comments, discussions about the 5-number summary? And you'll typically use StatCrunch to calculate this for you. Earlier, we looked at the tool Summary Stats, and all 5 of these are on the list for Summary Stats. So when you went to Summary Stats to get the mean or the standard deviation or the mode, the 5 number summary points are on there as well, and you can select those and it'll calculate them for you for a data set. So they do an example, which we will skip through, min and max, and then the quartiles. And then the last thing before we go to take a look and see if we could see what the homework looks like for section 3, we got 13 minutes or so, is we want to introduce the box plot, or sometimes referred to as the box and whisker diagram. So a box plot is a graph. So it'll be under the graph tab in StatCrunch. There's a choice for box plot. It's a graph of the data set that consists of a line extending from the minimum value to the maximum value, kind of like imagining a number line. So let's say you had here a line, and down here you had the min, and up here you had the max, whatever those were. And the box with lines drawn at the first quartile and the median and the third quartile. So let's say Q1 is here for my picture. Let's say the median is here, which is Q2. And then let's say Q3 happened to be over there. Then what you would do is you would draw lines across these and you would draw a box. And that makes a box plot. And of course, StatCrunch will do that for you. So this gives you a visual impression of the range of the data values and also where each 25% grouping of the data falls. And maybe you can say, oh, well, there's a little bit more of a spread in the next 25% of the data above the median than below, because the right half of the box is a little bigger than the left portion. So that's called a box plot. So they basically say how you would make it, the way I was just doing it. And then they take their same data set, they take their 5 number summary, and look how the box plot turned out for that one. So from our earlier discussion in the question, we could see, for example, that this data looks like it's skewed right, because the bulk of the data is lumped over to the left, but there's a long stretch on the tail out to the right. And the box plot helps us to see that. And it kind of also shows us that the first 75% of the data is all kind of spread sort of equally in the range of values between almost 0 and up to 21. It looks like there's about 7, a range of values of 7 in each range, but then the top 25% gets stretched way up and flies up like 50 points above that. So it's a nice visual way to get an impression of the distribution of the data. And there's that skewedness that we talked about before. Can be skewed. Finally, there's a definition of outliers, and that's why I said you need to know that inner quartile range, because it's in there. You're basically looking for data values that are 1.5 times the inner quartile range above Q3 or below Q1. I'm just saying it, they'll describe it, they'll show you an example. And a modified box plot is where you change your graph a little bit to show outliers, and StatCrunch will do that too. All right, so we're down to our last 10 minutes. I know we were a little rushed at the end there, but that did get to the end of what they wanted to show us.